So you need a bowl of water, and your first little activity, which hopefully, if you were here last week, isn't too hard, is just put these power station stages in order. So you've got the sentences, which turns into steam, steam pushes against a turbine, it heats up water, turbine spins around, coal is burned, turbine spins generator, which produces electricity. Can you put all those in order? While I fill a bowl with water. Have you done it? Oh, another person here, that's nice. You found us. Phew. Yeah, Facebook goes wrong a lot. YouTube doesn't go wrong very often, but when it does, it's much more stressful than when Facebook goes wrong. All right, are you happy with that? Let's have a little look then. Let's remind ourselves of what's going on inside a power station, because we learned about that last week. Right, here's a power station. Here's all those stages that I told you about. So this is a power station that burns coal, yeah? Like fossil fuels. The stages are, the coal is burned. That's the first one. The heat energy, which was trapped in the coal, not trapped in, you know what I mean, stored in, then heats up the water. The water turns into steam. The steam pushes against the turbine, that's this thing here, and the whole point of that turbine is to spin around so that it makes something inside the generator spin around. And we haven't really talked about what the generator does. We will do that in later lessons, but the important thing to remember is that when something inside the generator moves, it could spin, it could move up and down, as is the case later. That produces electricity, all right, or generates electricity, if you like. So that's how we got. That's where we got to last week. And then we said, well, fossil fuels like oil and coal and gas, they release a lot of carbon dioxide into the atmosphere. They're going to run out. It'd be better if we didn't use those. You could just not even bother with the coal and heating up the water and the steam. And you could just skip straight to the turbine. Remember we looked at wind turbines? So the wind turbine turns something inside the generator and that produces electricity. And we also looked at geothermal as well, which is where you just put water into the ground and it gets hot and that turns into steam and that pushes the turbine. So again, well, I was going to say no carbon dioxide emitted. That's not true, is it? We've found that there is carbon dioxide and other gases in the earth that this process does release into the atmosphere, which is kind of bad. So we've done all these ones. Describe how useful energy may be obtained or electrical power generated from chemical energy stored in fossil fuels, chemical energy stored in biofuels, which you only actually need if you're doing the Cambridge specification, and geothermal resources and wind energy. Right, today we get to look at, yay, how you generate electricity from water, waves and tides and dams. So we'll do all that today, but we'll start with waves, all right? First question, what causes waves? What does cause waves? Don't be embarrassed if you don't know this. It's an obvious one, but it's quite tricky actually. What causes waves? If you've got a bowl of water with you, can you please, well, maybe don't pick up the bowl of water. You could leave your bowl of water on the table, but have a look at your bowl of water. Imagine it's the ocean. What are you going to do to your bowl of water to make waves? In the correct scientific way. How are waves formed? Why are waves? What causes waves? Do something, please, with your bowl of water to make waves happen. This was really annoying people on Facebook yesterday. Are you doing something to your bowl to make waves? Is it the correct thing? Is it why ocean waves form? There's a couple of different things you can do. People on Facebook were starting to talk about the moon and the sun. To be scientifically accurate, you should really be blowing on your bowl. Yeah, satisfying. That is what makes waves. It's the wind, isn't it? If you've been coming to my all ages weather lessons, you know that really the wind is caused by the sun. So you don't need to remember all of this for IGCSE, but the sun heats the air above Earth and those air particles sort of spread out, get warmer, and then they move to areas of different pressure. You've got to remember that the sun heats the air, and the air moving is what the wind is. So in the end, what causes waves is the wind, and what causes the wind, but actually what causes wind is the sun. Which you do have to remember, because obviously they might ask you things about like what energy stores are associated with wave power. So you need to know, okay, waves are actually caused by the sun. But more on that in a little bit. All right then, have a go at this question. Oh, if you've been to the waves lessons, if you're following the whole syllabus with me, you might have learned about waves with me. Can you remember the answer to this? This is a toughie. Which turbine is going to harness the most energy from these ocean waves here? So we've got a wind turbine that is at 90 degrees to the ocean floor. We've got a wind turbine that is parallel to the ocean floor. And we've got a wind turbine that's on a diagonal. Which one of those, which way are you going to angle your turbine if you want to harness energy from these waves? Put a slightly different way to give you a bigger clue. You want something to push on the turbine, right? That's how the turbine's going to spin round, is by stuff pushing on it. Which way are you going to angle that turbine so that the water particles are pushing on the turbine? It's a good question, isn't it? I mean, actually, if you've not studied waves yet, it's a rubbish question because you just wouldn't know. But if you've studied waves, it's very good revision. The answer is, if you picked one, it's the middle one. Oh! You remember that ocean waves are transverse? It doesn't matter if you don't know this, you can learn it later. But a transverse wave is a wave where the energy moves from like side to side, you could say. But the matter, the actual water particles in this case, are moving up and down. You picture a boat on the ocean in a really big storm, the boat will be frantically tossed up and down. A boat in a storm doesn't end up just kind of whizzing from one side of the sea to the other side of the sea because it's being carried by water particles. No, so the water particles go up and down, so you need to put your turbine in the correct position so that the water particles push against it, right? There's actually loads of different ways you can get energy from waves, and all the technology is very new. I don't think, as far as I'm aware, anywhere at the moment, certainly in the UK, any kind of machine is being used to get electricity from waves that anyone is using. But there's a few very cool ideas out there. One of them is, well, I've sort of sketched it for you. This thing called the point absorber. So you've got a buoy, right? The sort of buoy that floats on top of the sea. It's actually attached to the sea floor, and it bobs up and down because that's the way that the water particles are going. And it's attached to a generator, so it makes something inside the generator move up and down, and for reasons which we will get to in later lessons, electricity is generated. Yeah, so you don't even need a turbine. It's just a buoy connected to a generator. You've got this cool light on the top which flashes to warn passing ships of where it is so they don't crash into it. That's pretty good, isn't it? Go on, tell me some advantages to that. Thinking about last week, you remember Phil Mitchell, that guy from EastEnders, that his ex-girlfriend admitted to killing him and loads of people tuned in to watch, and it used a lot of energy. What are the advantages to this kind of way of generating electricity compared to, say, wind turbines or oil or coal or gas? I'm going to actually count 20 seconds. I want you to write down as many as you can remember. I'll do this a few times, so don't worry if you're a bit rusty. You'll get it by the end. Six seconds. Scribble. A lot of the words begin with an R, we realised on Facebook yesterday. All right, so one of them is renewable. Remember, a renewable resource means it's not going to run out. So seawater is not going to run out, so that's good. Unlike, say, fossil fuels, which are running out fast. gives off very few polluting gases while it's working. You would be allowed to say like no carbon dioxide given off. And it's very reliable, right? It's always available. So if someone gets shot on some big TV program and everyone wants to watch it live at the same time, you know that there's going to be energy there. It's not like the wind where it might not be blowing at that time. That would be bad. Disadvantages, I'll just tell you these ones. It's a very new technology, so it's really expensive. Like kind of in the same way that not everyone is driving an electric car at the moment. Here is a beautiful picture of one of something that was designed for harnessing energy from waves. It's called... is it Pelamis or Pelamis? It looks like it should be Pelamis. I'm going to call it Pelamis. It's this huge kind of... Well, it actually looks like a sea snake. It works in a similar way to the method that I just showed you. Look at it rearing its head out of the ocean. Isn't that beautiful? It is named, in fact, after the yellow-bellied sea snake. It's kind of a similar shape. It moves up and down and generated electricity that way. Sadly, the company ran out of money and it all got taken apart. So, I don't know, you're probably not likely to get any questions on that, but it's interesting to see a real example. All right then, let's see if you can do this. This is quite challenging. Just as we finish waves, I've reminded you of all the different ways that energy can be stored here. Kinetic, gravitational potential, chemical, elastic, nuclear, electrostatic, internal, thermal, don't say heat, but you know what I mean, internal, thermal, and magnetic. And the pathways, how energy shifts from one store to another. It could be mechanically, just any kind of force, like a push or pull, or it could be electrically, or it could be by radiation, like waves, or it could be by heating because of a temperature difference. So what I'd like you to do is you've got a sort of, a very simplified flow diagram here with the sun at the top, and I'd like you to write the stores in the boxes and the pathways on the lines. So I've done the first one for you because we haven't really talked about this yet, that the sun is a nuclear store of energy. And how does energy get shifted from that nuclear store to the waves? I'll kind of give you two answers for that one. There's a kind of main pathway that should go on that line. How is the energy stored in the waves? What kind of energy store is waves? Are waves? How does energy get transferred or shifted from the waves to the generator? Is it mechanically, electrically, by radiation, or by heating? And how does energy get shifted from the generator to the national grid? The national grid is just, all the wires, if you like, between the power station and the house. Again, we'll talk more about the national grid later. Again, there was a beautiful mixture on Facebook of people who got it straight away and the people who weren't sure. I'd sort of prefer you not to be sure, because then it means, there's a point to my job. If anyone saw Lego story time this afternoon, I'm just thinking about clearing up some golden syrup. Oh, that was a mistake. I'm just going to leave it. How have you got on? I'll give you 10 seconds. All right, so how does energy move from the sun to the waves? Well, I mean, it'd be all right if you said heating, because there is obviously the air does get heated up because of a temperature difference, like the warm air kind of heats the cold air. But really, we will talk all about this later actually, so don't worry if you don't know this. But there are no particles in space. So heat can't travel from the sun to the earth just by kind of particles knocking into each other and passing heat along, which we've looked at briefly before. So it has to be radiation, and it is. Radiation shifts energy from the sun to earth, including the waves, and the waves are moving. So they are a kinetic energy store. And how does that energy get shifted from the waves to the generator? Well, that is mechanically, it's a mechanical pathway, because it is just a push and a pull, isn't it? That's what's happening inside the generator. And then that push and a pull caused by the waves is allowing the generator to shift energy via the electrical pathway to the national grid, eventually our homes. Is that all right? Let's move past waves now. Did you get that? So the sun is nuclear, and then it's radiation, kinetic, mechanically, and electrically. Moving on, so we've done waves. Again, you probably won't get that many detailed questions on them because, although now I've said that, you might, because it is a very, very new technology. We're not really using it yet, but the next two are far, far more popular right now. Let's have a look at tides. What causes tides? What causes the tides? What does cause the tides? On your PDF of homework, I will link you to a video where people explain some quite surprising thing about the tides. What causes the tides? You know what the tides are? Sort of the oceans going in and out. And in. If you live by the sea, you look at the sea, you watch it for a day, the sea will sort of come up to you, and then the sea will go far away again. Those are the tides going in and out. It's actually not what's happening. What's happening is that Earth is turning into the sea. But anyway, I'll link you to that video. What causes the tides is the moon's gravity. The tides do have something to do with the moon. It's the pull of the moon. It is also the pull of the sun a little bit, the sun's gravity. But I almost don't want to tell you that because you don't want to really start saying that the tides are caused by the sun because you might get confused and think that it's been heated up. It's not. The tides have nothing to do with like heat energy hitting them. It's just the, well, again, we'll just stick to the forces of gravity, mainly of the moon, causing the tides, okay? So here's a picture of how we do actually right now produce electricity using tides. You got the ocean. You just kind of block it off, right? And you've got a turbine down here. So when the sea comes in, then it pushes on the turbine one way. And when the sea goes out, it pushes on the turbine the other way. Come on, tell me some advantages. You should be able to spot quite a few advantages. Think of your R words, children, and some other words. What are the advantages to this? Just block off a bit of the sea. Tide goes in, tide goes out. Turbine spins. I will give you 20 seconds. Now there's only 19. Now there's 18. I'll stop talking, but you've only got 17 seconds left. I'm not drinking out of a bowl. You're drinking out of a bowl. Did you get any advantages? Yeah, come on, renewable. Because again, the seawater isn't going to run out, is it? There's no polluting gases given off. No carbon dioxide, so that's good. Again, someone on Facebook was picking me up and saying, well, it's while they're running, because you're probably going to give off some carbon dioxide in the factory making all these different bits. But yeah, while they're running, no polluting gases given off. They're very reliable. They're always available, unlike, for example, the wind. And they also produce loads of energy. Compared to some of the other methods, they produce loads and loads of energy. I asked a question on Facebook yesterday that I hadn't planned to ask, and it had everyone like really thinking and annoyed. So I'm going to ask you, why do you think that generating electricity using water generally produces more energy than generating electricity using air? Why does a wind turbine not produce as much, not generate as much electricity as like this turbine, which is in the sea? Why does a turbine in the sea produce more energy than a turbine that's been pushed by air? Smoke teacher face. Go on, try and think of an answer. Try and say something out loud while I'm doing a rubbish sketch on the board. So people on Facebook yesterday were saying things like, more force? Yeah, why more force though? Why more force? I mean, there's a lot of answers to this question, but one of the answers is, again, we will actually learn about it in the next module, actually. We're looking at solids, liquids and gases. The answer is air particles are quite far apart, aren't they? Whereas particles in a liquid, they're much closer together. In fact, they're touching each other. So you've got more force because there's just more particles pushing on the turbine, right? Air particles, just not as many particles because they're further spread out. Water particles, much more densely packed, so more particles. So it is more force, but it's because water is denser than air. Again, more of that later. Whoa, what's happened here? Right. Have a think about the disadvantages then, please. I reckon you can do this now. Give me some disadvantages. This is hard actually, isn't it? Disadvantages. They don't release any damaging gases. It's super reliable. You can have it whenever you like. What could possibly be the problem with this? Might help you to think about geothermal from last week. The answers are, there's not many suitable locations, like with the geothermal. There's not many places where it's going to be convenient to block off the sea and have it pass in and out of the turbine. And it can be harmful to wildlife as well. So yeah, there's loads of advantages to tides. One of the main things is it is incredibly reliable. I mean, you can literally set your watch by the tides. Waves, they can be bigger or smaller depending on the conditions, but the waves are always going to the tide's always going to come in, the tide's always going to come out at exactly the right time. But yeah, it can, obviously blocking off a bit of the ocean can be harmful to animals, particularly migrating animals. Right, let's have a look at the last one, which is damming. It's like damming things. It's not damming, although maybe it's damming. Let's see. Here's one. It's very similar actually to tides, but there are a few differences. So yeah, you just build a big dam. So there might be a river flowing and you just block it off. So you end up flooding a large area. What was a river now becomes a huge reservoir. And you let what was potentially the river trickle through, which turns a turbine. You can see the generator above it there. And you get a reservoir on the other side as well. So here's a proper picture. This is Gordon Dam, hydroelectric power plant in Australia. I mean, some people might think it's pretty beautiful. It's an incredible feat of engineering, isn't it? Wow. That is big. So you can see this was a river, which has presumably been expanded by humans because this enormous dam has been built. I don't know how you even begin to do that. And then there's turbines down here where the water is trickling through. It's very easy to say, oh, it's harmful to wildlife. Let's actually picture this wildlife, shall we? This is the Irrawaddy dolphin. Obviously, building a dam across rivers is not a good idea if you're an animal that migrates. So the Irrawaddy dolphin migrates along the Mekong River, for example, in Cambodia, and it's not having a nice time because humans are damming where it lives. Also, the potentially less cute, but the sturgeon as well is not having a good time, because it migrates. Give me some advantages though. Again, just 20 seconds, scribble them down. Hopefully they're sort of starting to flow a little bit more easily now. Some of the advantages to building a dam across a river and letting the water that trickles through turn a turbine. You got 12 seconds. I think there should be 4 fairly obvious ones, should there? All right, did you get your R's? Is it renewable? Yes, it is. Seawater, not going to run out. Is it reliable? Yes, it is. It's always available. There's no polluting gases given off. And again, it produces a lot of energy. But what are the disadvantages? Go on, 10 seconds. I think you should be able to come up with 2 actually. Have you thought of them? There's not many suitable locations. And it is harmful to migrating wildlife. And also, and this is the big one, it can involve flooding a really large area, which is bad for humans if they happen to be living there. They'll have to leave their homes, and also very bad for wildlife that maybe used to have a habitat living on the land and aren't suited to living underwater. All right then, have a go at this massive sheet for me here. So we'll skip waves, like I say, because it's not as common, the technology. But here's tidal power, the tide flowing through a turbine. Here's hydropower, river water flowing through a turbine. Can you tell me, please, what do they have in common and what is different about them? They don't release pollution while running. Is that the case with tidal power or hydropower or both? If you've been to my Facebook group and you have downloaded this worksheet, you can just be quickly like circling or pointing. You might want to make notes. But this is always going to be stored on YouTube. If you haven't got the sheet, you can think it in your head. It's up to you. Their energy comes from the sun. Is that the case with tidal power or hydropower or both? Which one's reliable or both? Which one's renewable or both? No need to transport fuel. Large area might need to be flooded. Hard to find places to put them. Very expensive to build. And they harm migrating animals. Which ones do tidal power apply to? And which ones apply to hydropower? Hydropower is damming, right? Like hydroelectric dam. Right, have you done it? Let's go through the answers. What do they have in common? Well, they don't release pollution while running. That is true of both of them. In fact, I should say, both these are particularly good in that area. The very, very few, got a very low carbon footprint, you could say, both tidal and damming. So that's true. They both harm migrating animals. That is also true. I've never seen a mark be given for that at IGCSE. It's worth knowing, but if I was going to write that, I'd probably add another disadvantage as well, just in case. They're both very reliable. They both use renewable energy. It's hard to find places to put them. Large area might need to be flooded. Well done if you got that. That's only with the damming method. It's obviously not the case with tides that you flood a large area. The sea is already there. And their energy comes from the sun. That is not true of tides. In fact, you had to kind of think about that. You had to sort of know what causes rivers, really, to get that one right. So you kind of had to know geography. But yeah, the sun heats up water, water evaporates, gets carried onto land, falls as rain, and that's how rivers flow, right? Did you know that? That the sun heating water, the water cycle that I don't need to teach because I'm a physics teacher. The water cycle means water gets up high and then it flows down low. So rivers, and therefore the damming method, they generate electricity ultimately because of the sun warming things up. But tides, remember, is the kind of sort of the push and pull, if you like, of the moon's gravity mainly. So the energy comes from the sun. That is only the case with the damming hydroelectric dams. And they're both very expensive to build. They're both sources of renewable energy, and you don't need to transport any fuel with both of them. So that's good. Sorry, I should maybe keep that up a little bit longer. Right, as I say, over on my Facebook page, there is currently... it's not worked again. Oh well, you know that that's both, don't you? There's currently a post saying, if you're watching live on YouTube, come over to Facebook and say hello. But we had quite a few difficulties, didn't we, on YouTube with the start of this lesson. So there might be some people there who've also just gone to complain or shout. Where is it? I can't find it. So I'll go over to Facebook now and see how many of you managed to find this lesson. If you want to support me, you totally can. How it works is, everything that I do is free. If you come to these IGCSE lessons, you not only get the printouts, but you also get a PDF of homework, which I will put together literally as soon as I've finished this video. I'll go and put together a link of all the past paper questions that I've found that I think you should be able to answer after this lesson. And also maybe just some interesting little links to videos as well, like what really causes the tides and that kind of thing. And I found a really good page with all the different ways that you can get energy from waves. So all that I think will just be good for you to read. It just help the information stay in your brain. If you want to pay me for doing all that work, you can. In fact, somebody has to, or I would not be able to teach these lessons. So I've actually had 3 new sign-ups today and yesterday, so I need to post these out. So you too could be sent one of these envelopes, which I've been super organised and put together in advance. If you sign up to support me with £5 a month, I send you Theatre of Science magazine. If you sign up with 5, you just get one on mould, and you get a free plastic bag which composts so that you can grow your own mould and identify it. And if you sign up with £6, you also get the latest magazine, which is about weeds. I think they're suitable for all ages. Certainly I did not know any of the information in the magazines before I wrote the magazines. And I've got a science degree, so, if you're a bit older, hopefully I think you'll still find some things in there that interest you. And the rainbow glasses, they're actually diffraction glasses. So again, very, very relevant to GCSE. Right, let's go over to my Facebook page and see what's going on. Again, I was apologising at the start of this lesson. If you have commented on my Facebook page and I've left you what looks like quite an abrupt message, it's because the spacebar is broken on my computer. I have no spacebar. So that's limiting my communication somewhat, which is why I've maybe just posted you a link instead of what I would usually do, posting you a link and saying, here you go. Right, let's have a look and see. Hopefully you've all found me. Oh, David's here. Phew. Hiya, David. You made it. Oh, that's good. Let's see who else is here. Oh, no. Yeah, and Matthew's here. That's good. Just clicking all comments. If you have not left me a message on Facebook, you can totally go. This is it now. Matthew is here. David is here. Hopefully Rachel and Lois found it. We're finally here. That's good. Oh no. Okay, well, thank you for coming, you lot. Thank you so much for persevering. I know that we have been having some problems recently. This was a whole new problem to do with YouTube, just changing some things. Just when I came to log on, it looked slightly different and ended up sideways. So this isn't an internet issue. Actually, it's a whole new fun issue related to working on the internet. All right. I'm going to go. So we've only got 1 week left now until I take a week off for half term. So we've only got 1 week left of this whole energy topic. And then we move into another module about, which is it's very similar actually, but about temperature, solids, liquids and gases, lots of stuff to do with heat and convection and conduction, lots of really good activities. I'm quite looking forward to this next module of lessons. And then we've only got 3 modules left, I believe. We're doing radioactivity and all sort of nuclear things. We're doing a bit of astronomy right at the end, and we've got this next quite a big module on energy, like temperature and particles and stuff. Bye, Matthew. And then that's it. Spooky. I don't know whether we'll get the whole way through everything by next summer, or whether maybe it'll have to be the year after. I will find time to plan all the way to the end as soon as I can, so that I can let you know. But hopefully, you're getting something out of these lessons, even if we can't see the end just yet. Right, I will go. Thank you so much for going. I'll see you very soon. I'll go and post my stuff and make your homework. See you next week. Bye.